Hello and welcome to MyScience Tutorials. In today's video, we are going to be looking at capacitors or network of capacitors. Before we begin, if you are new to MyScience Tutorials, kindly consider subscribing and pressing that notification button so that you don't miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So let's go ahead. What then is a capacitor? A capacitor is a device used for storing electrical charges or energy. The measure of the ability of a capacitor to store a charge is called its capacitance. The capacitance of a capacitor, C, is given by the ratio of the charge on the plate to the potential difference between the plates. So, the capacitance of a capacitor is equal to what? The charge divided by the potential difference across the two plates. So this is the charge represented by what? Q, and then the V is the what? The potential difference. All right, so from here the SI unit, okay, of the capacitance is what? Coulomb per volt or farad. Now let's take note of these conversions. If we have 1 microfarad, this is equivalent to what? 10 raised to the power 6 farad, -6 farad. If we have 1 nanofarad, we mean 10 to the power 9, -9 farad. And then when we have what? 1 picofarad, it means 10 raised to the power -12 farad. These conversions are really important, and we tend to use them a lot when dealing with capacitors. So let's go ahead. So we want to look at what? Capacitors in parallel. So let's have a look at this diagram. So we have one capacitor here, another capacitor here, another capacitor here. This diagram is not drawn to scale, so don't mind my sketch. Then we have a potential difference or an electrical source applied to it. So we have the charge flowing through, and then it is being divided over here. So here is Q1, this is Q2, this is Q3, and then they all meet at this junction to become a normal Q, and then we have the potential difference V over here. So from here we can say what? The charge in the circuit, the charge in this circuit Q is equal to what? The sum of what? The charges across all the three capacitors, that is Q1 plus Q2 plus Q3. But we know what? From what? Capacitance is equal to what? The charge over volume. It means what? The charge is equivalent to or equal to what? The capacitance multiplied by the volume, or sorry, the voltage or the potential difference, which is V. So it means our Q over here becomes what? CV is equal to what? C1 V1 plus C2 V2 plus C3 V3. Now the potential difference move across the capacitors. Now the potential difference that moves across the capacitance is equal, or our V, or the potential difference that will move through the capacitor 1 over here, is the same as the same potential difference that will move through the second capacitor, and the same potential difference moves across the third capacitor. So it means what? V1 is equivalent to V2 and is equivalent to what? V3. So if that is true, it means what? From here you can write CV is equal to what? C1V plus C2V plus what? C3V, because the V are all equal. So CV is equal to, we can factor the potential difference out over here, then we have C1 plus C2 plus C3. So if we divide both sides by V, then we get our capacitance to be equal to what? The sum of the individual capacitance of the capacitor in the circuit. So when we have capacitors in parallel and we want to get the overall capacitance of the capacitors in the circuit and they are connected in parallel, we just add the individual capacitance to get the overall total capacitance of the network. Now let's have a look at capacitors in series. So let's consider this diagram. So we have three capacitors connected to what? Source of voltage. We have the charge Q, and then we have V1, V2, V3, and then we have V. From here, we can see that the charge that goes through this circuit is the same charge that is coming out of the circuit, but then the voltage across the capacitors is being shared. So it means the overall voltage in capacitors connected in series, the overall voltage is equal to the sum of the individual voltages across each capacitor, that is V1 plus V2 plus V3. But we know that V is equal to what? Q over C. So it means our voltage over here, if we substitute the voltages by this formula, we get Q over C here is equal to what? Q1 C1 plus Q2 C2 plus Q3 C3. But for capacitors in series, Q1, the same charge flows through the capacitor, so Q1 is equal to what? Q2 and is equal to what? Q3. So if that is the case, it means our Q over C is equal to what? Q over C1 plus what? Q over C2 plus what? Q over C3. So from here, we can factor out what? Q over here. So we have Q over C is equal to Q into bracket 1 over C1 plus 1 over C2 plus 1 over C3. So from here, we can see that QQ is common over here, or let me factor this out as well. So I have Q into bracket 1 over C is equal to what? Q 1 over C1 plus 1 over C2 and 1 over C3. So if we cancel out the Q because they are equal, we have what? 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So this means for capacitors in series, if you want to get the overall capacitance of the capacitors in the network, we just have to add the inverse of the capacitors in the circuit. So the overall total capacitance for capacitors in series is what? 1 over CT, where CT is the total capacitance, is equal to the sum of the individual capacitors, the inverse of the individual capacitors that we have in the network, up to what? 1 over what? Cn, where n is the what? The last number of capacitor that we have in the network. So with this basic introduction, let's have a look at how to calculate the energy, stored in a capacitor. So let me do that quickly here. The energy stored in a capacitor can be calculated by what? Half CV squared. So this is also very, very important. So if you want to find the energy stored by a capacitor, you just multiply what? Half by the capacitance of the capacitor multiplied by squared the voltage across the capacitor. So let's have a look at some examples. So we have the diagram below shows a combination of capacitors. If the potential difference across A and B is 10 volts, calculate I, the capacitance of the equivalent capacitor, II, the charge stored by the capacitor. Alright, so let's go ahead. I. So they said the potential difference across what? AB over here is equal to what? 10 volts. So we have to find the capacitance of the equivalent capacitor. Now we can see that we have two capacitors connected in parallel, and then this parallel is connected in series with this one. So first of all, we need to solve the ones that are connected in parallel so that we get it to be in series with the second one, and then we can find our total capacitance. So first of all, we add these two. So I will make it C1 is equal to what? The 5 microfarad plus 15 microfarad. We are just adding them because they are in parallel, and we just learned that capacitors in parallel, we just add the individual capacitance to get the overall capacitance. So this is equal to 20 microfarad. Okay, so now that we have 20 microfarad over here, it means the overall capacitance for these two combination is 20, which is now in series with the second 20 capacitor that we have over here. So it means our C total for this one will not be 1 over C1 plus 1 over the 20 microfarad capacitor that we have over here. So it means our total capacitance for this will be 1 over 20 microfarad plus another 1 over 20 microfarad. This is equal to, this is 20, and then this will be 2. So it means our capacitance, or CT, total capacitance, will be equal to the inverse. This is 1 over this, 1 over this, 1 over this. So this will be the inverse of this. So we have 20 divided by 2 to get the C total, which is now equal to 10 microfarad. Now the 10 microfarad can be rewritten as 10 times 10 raised to the power minus 6 farad. Let's take note of that. Okay, so the second aspect of the question, II, the charge stored by the capacitor. Charge, we know charge Q is equal to the capacitance multiplied by the voltage. So it means our capacitance over here, which is 10 times 10 raised to the power minus 6 multiplied by our voltage, which is 10 volts, or the potential difference. So this is equal to 100 times 10 raised to the power minus 6. So our charge stored by these capacitors is equal to 100 microcoulombs. Alright, let's have a look at another example. Example number 2. Calculate I, the total energy stored in the capacitors. II, the work done by the battery in charging the capacitors in the following circuit. So we have to calculate the total energy stored in the capacitor. So energy stored in the capacitor. Now we said the energy stored in the capacitor is half CV square. So it means we need the overall total capacitance of this network before we can be able to compute the energy stored. So we have 4 capacitors, 2 of them, they are both paired 2 parallel, and then the paired ones, the parallel ones, are in series with each other. So first of all, we need to, let me name this one C1, this is C2, C3, and then C4. So if we add, first of all, to get the total capacitance over here, we add C1 plus C2, which is equal to 15 microfarad plus 25 microfarad, and this is equal to 40 microfarad. We are adding them straight because they are in parallel. Now the second one, this C3 plus C4 is now equal to 20 microfarad plus 30 microfarad, and this is equal to 50 microfarad. Now if C1 plus C2, let me say this is A and this is B, our overall total capacitance for this network will be 1 over CT. Let me write this somewhere else. 1 over CT, which is the total capacitance, is equal to, because These two are now in what? Series. After we've computed the total for this, they are now in series. So we add 1 over what? A, which is what? The result from adding C1 and C2, plus 1 over B, the result from adding what? C3 and C4. So we have 1 over Ct is equal to 1 over 40 microfarad plus 1 over what? 50 microfarad. So 1 over Ct is equal to, we have this 200 microfarad as the LCM. This will go here 5 times, multiplied by 1 is 5, plus this will go here 4 times, multiplied by this is 4. So we have 1 over Ct is equal to what? 9 over 200 microfarad. Okay, so to get the total capacitance, we invert this. We have 200 microfarad divided by 9, and this is equal to what? 22.2 microfarad, or 22.2 times 10 raised to the power minus 6 farad. Okay, now that we have our total capacitance, we can now go and calculate the energy, which is now equal to what? Half into bracket the capacitance, which is what we have over here, 22.2 times 10 raised to the power minus 6, multiplied by the voltage is what? 10 squared, and then this is equal to what? Let me use another color for that. And then this is equal to what? 1.11 times 10 raised to the power minus 3 joules. So the energy stored in all these capacitors together, or in this network, is what? 1.11 times 10 raised to the power minus 3 joules. Alright, let's go ahead. Okay, so the second aspect of the question is saying the work done by the battery in charging the capacitors in the following circuit. So work done. The work done by capacitors in a network is equal to what? QV, where Q is the charge and then V is the voltage. So this is equal to what? We know Q is equal to what? CV. So we have what? Q, which is what? CV multiplied by what? V again. So this is what? CV squared. So our work is now equal to what? 2.22 times 10 raised to the power minus 6 multiplied by what? The voltage is what? 10 squared. So our work done over here is now 2.22 times 10 raised to the power minus 4 joules. So that is the work done by this entire circuit.